All right, so we're moving on in stats. We're moving on to our next chi-squared goodness of fit test, which is dealing with the normal distribution. So what we've looked at previously is that we've looked at dealing with an uniform distribution. So if everything's equal across the board, is it equal or not? And we also looked at it if it was a binomial distribution, which is using that NCR formula. So now we're going to be looking at using a normal distribution, so where it kind of looks more like a bell curve. That's what we're going to be doing. Okay, so we're going to look at chi-squared using that. So the hardest thing here is trying to find the boundaries for each normal distribution. So when we're thinking about a normal distribution, let's go back to when we talked about it originally, and let's think about the percentages. If we're dealing with one deviation on either side of the mean, how or what percent of the total data should fall within one deviation of either side of the mean? That's right. If you guys remember the empirical rule, it should be about 68. Okay, 2 deviations would be the next number in that, 68.95, and then the last one is 99.7. So 3 deviations of on either side of it should be approximately 99.7% of the entire data. So that's your empirical rule, trying to think back when we learned that, which is your 68, 95, 99.7 rule. Okay, so that's how much of the data should be on 1 deviation of either side of the mean, 2 deviations, or 3 deviations. That's how the spread should be. So we're going to see if that is true or not. Okay. So to do that, what we're going to do is that we're going to use our z-score. And we're going to calculate our z's using how we've always done it. X minus the mean all over the standard deviation. X minus mu all over sigma. Okay, those numbers haven't changed really much. And then what we do is we take our z-table, okay, that you should still have, and you're going to look at that to help you find the percentages. So remember, that z-table tells you the percent from the mean to that number that falls within the data. Okay, so that's what's going to happen. Okay, now we're going to look at this example. So the speed of a car passing an exit are put on this table. Okay, and what we want to know is are the speed of the cars as they pass this exit a normal distribution? And so what we have to find first is what percent should fall within each category. So what percent of the cars should be under 56 miles per hour? How much should be between 56 and 62? How much should be between 62 and 68? How much should be from 68 to 74? And how much should be over 74 miles per hour? And that's going to help us find our E's. These frequencies are O's, or are observed. Okay, so those are the O, the observed. So take a second to write down all this data. Okay, now we are assuming that the mean of this data set is 65 miles per hour, how fast you're supposed to go on the road. Now, the sigma on this one we're also assuming is going to be 6. These numbers are usually either given to you or you calculate it based on what's given. Okay, so now what we want to do is we want to find, using our z-score formula, we want to find what percent should fall into each category. Now, going back to the previous slide, those numbers 56, 62, 68, 74 are going to be the numbers that we're going to use as our x's. And then the 65 is our mu, and 6 is our sigma. So we find each one of those and we find each value. So for 56 it's negative 1.5, for 62 it's negative 0.5, for 68 it's positive 0.5, and for 74 it's a positive 1.5. Look at how nice that worked out. And so we use those numbers and then we go back to our sheet. Okay? And what we want to do is we want to find the percent that falls within each category. Now these are already calculated and based on it. So the negative 1.5 is 0.432. So that's what negative 1.5 is. It's that. Remember, it doesn't matter if it's positive or negative. They still are the same number. 0.5 is 0.1915. And then, as you see, it goes down and we calculate each one. These last numbers, all of these numbers, okay, all of those are your percentages for each category, okay? So the first category is less than 65, or less than 56. Second category is from 56 to 62. Third category is from 62 to 82. Next one's 82 to 74, and the last one's over 74. And what's basically happening here is that we're taking our normal distribution and we've divided it up into sections, okay, like this. As you see, we end up having 5 sections where the red lines divide, not where the mean is. We end up having 5 sections. Over here we have our less than 56. Over here we have our more than 74. And as you notice, if you look back at the previous slide, or if you look back at your notes, those are the exact same percentages. Same with 56 to 62 and from 68 to 74. Those are the same percentages. That's how a normal distribution should work. And the middle is the other one. So almost 7% should fall on either tail of it, 24% the next ones, and then 38% should fall in the middle. That's what we're basically trying to find. So now what we want to do is we want to find our expected. So now I've taken my table with the frequency and I've added what the normal distribution probabilities should be, which is what we just calculated. And as you see, if you add them up, you get it fairly close to 1. It won't be exact because of rounding errors, but you should be fairly close to it, either sometimes over or sometimes under. So now what we want to do is we want to find our expected. And to find our expected, what we're going to do is we're going to take this number, 175, and we multiply it to all of those. And that's how we get our expected. 175 times 0.0668 get us about 11.69. Multiply it by the next one should get us about 42.3, yada, yada, yada. Okay, so we get all of our numbers. Okay, so that's how we get our expected. Now, once we have our expected, we can move on and do our actual distribution. Okay, so when we do our distribution, step 1 is what? Null hypothesis. Yes, it's our null hypothesis. So we're going to find our null hypothesis. Okay, so we're going to find our null hypothesis and our alternative hypothesis. Remember, our null hypothesis is always going to be whatever the distribution is. So if we want our distribution to be a normal distribution, that means that our null hypothesis is going to be that the speed of the cars are normally distributed. And our alternative hypothesis, or our H1, would be that the speed of the cars are not normally distributed. Okay. Okay, step 2, which I don't think I mentioned earlier in the problem, is your alpha. Alpha is 0.05. Again, if it's not mentioned, you can pick your own, but in this case, let's just use 0.05, so we're all the same. Step 3, what type of test are we using? Don't say Z, don't say T. It is a chi-squared with normal distribution. Okay, so it's a chi-squared test because we're trying to find distribution, and then you mention which distribution you're dealing with. In this case, a normal distribution. Okay, remember when we talked about uniform or binomial, we mentioned those as well. So that's your steps 1 through 3. Step 4 is your critical, which remember we usually do our drawings. So we have our drawing like that, and then we want to find our number. Now, how many categories were there for this problem? If you're trying to think back, if you look back at your notes, there was 5. There was 5 categories: less than 56, more than 72, between 56 and 62, between 68 and 74, and then the one in the middle. So we have 5. Remember, go back to your chi-square sheet. Okay, go back to your chi-square sheet, and you want to find what the number is. So first off, what is the degree of freedom? And you go, the degree of freedom is 5 minus. That's 4. Yes, it is 4. So your degree of freedom is going to be 4, and then you look at your 0.05, which gets you a 9.488. So that's your critical chi-square value, is that number. Okay. Next up is your step 5, which is your statement. So your statement in step 5, you're going to start off by saying that reject the null hypothesis in favor of the alternative hypothesis if the chi-square value is greater than 9.488. So remember, it has to be bigger than it for you to reject it. Otherwise, you fail to reject your null hypothesis. Make sure you write all that thing. You can use your inequality signs. You guys know all that stuff. Okay. After that, we go on to our math. Now our math, I have it set up with our table. Okay, so there's the speed of the cars, or categories, our observed and our expected. Okay, which we already calculated previously. So now we do O minus E, our observed minus our expected, which comes up right there. Okay, you see some of those are negatives, which are fine. Then we square each one of those numbers. Now when we square each one of those numbers, you see all those numbers turn positive, and that should be important. So all those are positive, and then what we're going to do is we're going to take each one of these numbers and we're going to divide it by these numbers. Okay, the one that falls in the correct one. So we'd go 69.06 divided by 11.69, and then we get our numbers: 5.91, 6 point whatever. And you see some of them are smaller, except for that last one. which kind of got away from us. And as we see, when we add all these up, we get 32.69, which puts us over our critical value number. So that means for our over onto step 7, when we state if we're going to reject or fail to reject, we would end up saying that we're going to reject this because our 32.96 ends up being larger than our 90 or 9.488. And because of that, we end up having our null hypothesis rejected by it. So then our step 8, which we state what's happening, we would say that our that this driving data does not fit a normal distribution. So we just say that the distribution of the speeds of the car is not normally distributed. Okay, so remember you have to tie it back in. Okay, so that wraps up our normal distribution chi-squared stuff. Everything should be fine. We'll be continuing on and doing a little bit more as we move on to our next sections.